Two colossal bubbles of energy tower over our galaxy. These are the Fermi Bubbles, erupting from the heart of the Milky Way and stretching for tens of thousands of light years. But they are not empty. Hidden within their vast glow are 30 distinct and bizarre structures, cosmic oddities that defy every explanation. By the end of this journey, you will see our galaxy's center not as a quiet place, but as a crime scene littered with evidence of a cataclysmic event. We will confront arches of pure gamma rays, spiraling filaments of power, and signals that could rewrite physics. What single force could have sculpted such a chaotic menagerie inside these bubbles? The first clue is a pair of impossible bridges. At the very edge of the northern Fermi bubble, astronomers found not a ragged frontier but an architecture. They are called the gamma-ray arches, and they are exactly what the name suggests. Picture two perfect, symmetrical arcs of the highest energy light in the universe, curving gracefully across the sky. Their scale is almost incomprehensible. Each arch spans thousands of light years, meaning if you could stand at one end, the other would be lost in the distance, a faint curve of pure energy against the black. This is not a messy explosion, it is a sculpture, and its smooth, unbroken curvature is the first major problem. We know of forces that can create structures in space, like shock waves from a titanic black hole eruption. But shock waves are chaotic. They ripple and break and form jagged edges like the wake behind a speeding boat. These arches are serene. They are too perfect, too symmetrical, as if drawn with a cosmic compass. Whatever event created the Fermi bubbles did not just blast material outwards. It somehow molded that energy at its outermost boundary into these vast, luminous doorways. They stand as silent sentinels guarding a secret about the force that placed them there. What kind of explosion writes in perfect circles, but the arches are merely the elegant frame? Inside the southern bubble, the scene turns chaotic, dominated by a single, twisting thread of raw power. This is the southern spiral filament, and it is unlike anything else in our galaxy. Picture a colossal, luminous rope tens of thousands of light years long, coiled like a spring deep within the bubble's glow. It is not a straight jet, not a scattered cloud, but a perfect helix. This shape is a screaming clue. In nature, a spiral that precise usually means one thing. It is tracing the lines of an invisible force. Think of iron filings aligning around a magnet. The helical path of the filament suggests it is caught in, and perhaps even made by, an immense magnetic field. But here the mystery deepens. We know magnetic fields exist in space, but the sheer energy required to light up this filament, to make it shine so brightly in gamma rays across such a vast distance, is staggering. It is as if someone took a cosmic lightning bolt and twisted it into a corkscrew. What natural process could both generate that much power and then sculpt it into such a graceful, ordered spiral? Known cosmic jets from black holes are powerful, but they are typically straight and narrow, punching through space like a laser beam. This filament is a tangled, energetic dance. It implies the original event that created the Fermi bubbles did not just release energy. It somehow braided that energy with magnetic forces in a way we have never seen. This single structure is a paradox, a ribbon of chaos wound into a perfect spiral, and it holds the key to understanding the turbulent forces still churning within these silent bubbles. Yet this spiraling filament of energy is not alone in its defiance. Deep within the base of the southern bubble, anchored directly above the galaxy's violent heart, lies a point of blinding intensity. Astronomers call it the central X-ray knot, and it is the brilliant, puzzling engine of this entire mystery. If the Fermi bubbles are the smoke, this knot is the still glowing ember of the fire. It is not a large, diffuse cloud. It is an incredibly compact and fiercely luminous concentration of X-rays, the kind of light emitted by matter heated to millions of degrees. Picture a single, searing white-hot coal suspended in the vast, cooler glow of the bubble's gamma-ray fog. Its location is the first crucial clue, sitting right at the launch point, the ground zero from which the bubbles erupted. This positioning suggests it is the ongoing power source, the active scar of the original cataclysm, but its nature is what breaks our models. Such intense energy in such a small space could be a concentrated shock front, a place where the outgoing wave of energy from the galactic center is slamming into surrounding gas with unimaginable force, compressing and superheating it into this brilliant pinpoint. That would be a natural, though extreme, explanation. However, the knot's sheer luminosity pushes the limits of that idea. It shines with a persistent ferocity that challenges the notion of a simple, fading echo. This leads to a far more provocative question. What if the knot is not just a remnant but an ongoing event? What if it is a continuous discharge, a kind of cosmic blowtorch that has been steadily fueling the bubbles for millions of years? This single, brilliant anomaly forces us to reconsider everything. Is the story of the Fermi bubbles a tale of one ancient explosion, or are we witnessing a permanent wound in the fabric of our galaxy, a leak from a realm of physics we do not yet understand? The brilliant knot at the galaxy's core offers a clue, but the true architecture of the Fermi bubbles is written in invisible ink, a script of magnetic force. This brings us to the fourth structure, the polarized radio lobes. While gamma rays show us where the energy is, radio waves reveal its hidden skeleton. Deep within the bubbles, astronomers have mapped vast, diffuse regions that glow not with visible light, but with a very specific kind of radio emission. This light is polarized, meaning its waves are all vibrating in the same, aligned direction. In the cosmos, that alignment is a signature. It is the unmistakable fingerprint of powerful, organized magnetic fields stretching across thousands of light years. Think of it like a vast, cosmic crime scene where every piece of dust has settled in perfectly parallel lines, pointing directly to the force that arranged them. These magnetic lobes are the enduring framework of the entire structure. They tell us the original event was not a simple fireball. It was a directed, magnetized eruption that left behind a permanent cage of force, a scaffold that still holds the bubble's shape millions of years later. The most logical architect for such a magnetic cage is our galaxy's supermassive black hole, Sagittarius, a star. In its active past, it could have launched jets or winds so powerful they carved these magnetic channels into the space around it, inflating the bubbles like balloons lined with iron filings. This fits the story of a past cataclysm, but here is the puzzle: the lobes are not chaotic, they are stable and smooth. If they were the turbulent aftermath of a sudden black hole feast, we would expect them to be twisted, fractured, and fading. Their current calmness is deeply strange. It is as if a hurricane passed through, and instead of leaving shattered wreckage, it left a perfectly preserved, silent cathedral of magnetic force. This forces a difficult question. Are we looking at the fossilized remains of a single ancient explosion, its magnetic fields frozen in time? Or is there some subtle, ongoing process, perhaps a steady wind from the black hole, that is actively maintaining this immense, organized structure, keeping the magnetic walls of the bubbles from collapsing? The polarized lobes are the silent, enduring bones of this mystery, and their very stability may be the most unstable part of our theories. These magnetic bones give the bubbles their shape, but what fills them with substance? Drifting through this vast cathedral of force are ghostly inhabitants, the high-velocity gas clouds. These are not mere wisps of dust. They are massive, dense clumps of hydrogen gas, some containing the raw material for millions of stars. Yet they are not peacefully floating. They are being violently hurled through space, embedded within the bubble's structure and moving at speeds that defy gravity's grip. Imagine finding a fleet of ocean liners in the sky, not falling, but racing upwards at thousands of miles per second. That is the scale of this motion. These clouds are caught in a cosmic hurricane propelled outward from the galactic plane. Their very presence is critical evidence, the tangible debris flung out by the event that created the bubbles. But this evidence has created a fierce debate, a mystery of origin that splits astronomers into opposing camps. Where did these clouds come from? The leading theory points directly to the galactic center. In this scenario, the same titanic explosion or outflow that inflated the Fermi bubbles also scooped up vast amounts of gas from the region around the supermassive black hole and blasted it outwards like a volcanic eruption carrying chunks of the mountain itself. The speeds and trajectories seem to support this, as if tracing a path back to a single, violent point in time. Yet there is a compelling alternative, a story of cosmic theft. Some scientists argue these clouds are not native to our galaxy at all. They could be the mangled remains of ancient dwarf galaxies, small neighbors that ventured too close to the Milky Way and were torn apart by its gravity. The Fermi bubbles, then, might have simply engulfed this pre-existing debris as they expanded, imprisoning the galactic wreckage within their glowing walls. This debate is not just academic, it strikes at the very nature of the cataclysm. If the clouds are from the center, they are a direct sample of the event's fuel and fury, a chemical fingerprint we can analyze. If they are cannibalized galaxies, then the bubbles are even more immense and powerful than we thought, capable of swallowing entire systems whole. These high-velocity clouds are the prisoners of the bubbles, and their origin story will determine whether we are studying a local disaster or a galactic conquest. The debate over the cloud's origin is a search for the crime scene's debris, but some evidence points not to the debris itself, but to the lingering energy of the weapon. This brings us to the sixth and seventh structures, a pair of ghostly twins known as the microwave haze patches. High above and below the galactic plane, nestled within the broader gamma-ray glow of the Fermi bubbles, are two vast, symmetrical regions that shine with a soft, pervasive microwave light. They are not sharp filaments or bright knots, but rather a diffuse, all-encompassing fog. This is the signature of something very specific, a sea of relativistic electrons. These are subatomic particles accelerated to nearly the speed of light, and as they spiral along weak magnetic fields, they give off this characteristic microwave hum. The existence of this haze is, in one sense, expected. A cataclysmic event like the one that forged the bubbles would have created a vast flood of these high-speed particles. The real mystery is not their presence, but their condition. For this haze to still be shining so brightly millions of years after the initial event, something must be keeping those electrons energized. Left alone, they would rapidly lose their speed, their glow fading into darkness like embers cooling after a fire. Yet the haze patches remain uniform and bright, a consistent fog bank of energy. This points to a continuous injection of power, a cosmic recharging station operating in secret. What could possibly be doing this? One possibility is a network of weak shock waves, still rippling through the bubble's interior like echoes in a canyon, giving the electrons a gentle, ongoing push. Another, more profound idea involves turbulence in the bubble's magnetic fields, creating a natural particle accelerator that steadily tops up their energy. But the symmetry of these patches is the final, haunting clue. They are mirror images in the north and south, suggesting the re-energizing process is not some random, localized chaos, but a fundamental and balanced property of the entire bubble structure. It is as if the bubbles themselves are alive with a low, steady current, a permanent whisper of power that keeps this ghostly haze from ever fading away. This persistent, low-energy hum of the microwave haze forms a quiet background, but the Fermi bubbles are also studded with points of fierce, concentrated violence. Scattered across their vast interior are three brilliant anomalies known as the gamma-ray hotspots. These are not diffuse glows, but intense, localized beacons of the highest energy light, shining with a ferocity that demands its own explanation. The first, and perhaps most puzzling, sits high in the northern bubble, far from the chaotic center. Its gamma-ray signature is a jagged spike on an astronomer's chart, a pattern of light that does not match the smooth curve expected from normal cosmic ray collisions. It is as if, within this one small region of the bubble, the laws of particle physics are playing by a different set of rules. This spectral fingerprint is the key. When cosmic rays, which are just high-speed protons and atomic nuclei, slam into slower-moving gas, they produce a predictable spread of gamma-ray energies. The light from this northern hotspot does not follow that script. Its energy is too concentrated, too focused in specific, unexpected bands. This forces a radical idea. Perhaps this hotspot is not a site of collisions at all, but a hidden particle accelerator itself, a natural machine far more powerful than anything on Earth, somehow operating in isolation thousands of light years from the galactic core. The second hotspot glows ominously at the base of the southern bubble, a searing knot of light where the outflow meets the dense gas of the galactic disk. Its location suggests a simple explanation: a cosmic traffic jam where the bubble's expanding energy slams headlong into interstellar material, creating a titanic shockwave that crushes particles to incredible energies. Yet, once again, the detailed spectrum of its light tells a more complicated story. While some of its emission fits the shock model, there is an excess, a stubborn surplus of gamma rays at very specific high energies that shockwaves alone cannot easily create. This surplus is the ghost in the machine. It points to an additional, unknown process at work within the chaos of the collision. One tantalizing, though highly speculative, possibility involves the deepest mystery in the universe: dark matter. Some theories suggest that when particles of dark matter collide, they can annihilate each other in a flash of pure energy, producing gamma rays with a very distinct signature. Could this hotspot at the bubble's edge be a window into that invisible realm, a place where the unseen majority of matter in the universe is meeting its end? It is a long shot, but the anomalous light refuses to let us dismiss it. The third major hotspot is not isolated at all, but seems intricately linked to the southern spiral filament, that colossal twisted rope of energy we encountered earlier. It appears as a brilliant bead strung along the filament's length, a point where the already immense energy of the spiral becomes blindingly intense. This connection is the critical clue. It strongly suggests that whatever process is energizing the entire filament, perhaps a wave of magnetism traveling along its length, reaches a fever pitch at this location. The hotspot may be a node, a cosmic transformer where magnetic energy is converted into particle acceleration with staggering efficiency. Unlike the other two, this hotspot's context provides a framework. We are likely seeing a natural particle accelerator in its most extreme and visible form, a place where the hidden magnetic architecture of the bubble reveals its power by focusing it into a single, brilliant point. Yet, even with this context, the sheer output is bewildering. It challenges our understanding of how efficiently such diffuse magnetic structures can concentrate energy. These three hotspots, each with its own strange story, prove that the Fermi bubbles are not a uniform fog. They are a dynamic landscape, dotted with factories of extreme physics that are working in ways we are only beginning to decipher. The brilliant hotspots show us where the bubble's energy is focused, but a profound silence at its edge speaks volumes. This is the mystery of the missing X-ray shell. According to every established model of cosmic explosions, when a structure like the Fermi bubbles expands into the thin gas of the galactic halo, it should create a brilliant telltale rim. Picture a soap bubble inflating in a smoky room, its outer skin gathering and compressing the smoke into a sharp, bright edge. In astrophysical terms, as the bubble's leading shockwave plows through space, it should superheat the surrounding gas to millions of degrees, causing it to shine brightly in X-rays. Astronomers have searched meticulously for this expected shell, scanning the outer boundaries of both bubbles with our most powerful X-ray telescopes. They found nothing. The predicted brilliant rim is simply not there. This absence is not a minor detail, it is a fundamental crack in our understanding. It forces a complete re-evaluation of three critical aspects: the bubble's age, their energy source, and the environment they inhabit. If the shock front was too weak to create a bright X-ray shell, perhaps the bubbles are far older than we think. Their expansion may have slowed to a near stop, the initial shock having dissipated long ago into a gentle pressure wave that no longer heats gas efficiently. That would mean we are looking at a fossil, an ancient structure whose violent birth occurred in a distant epoch of the galaxy's history. Alternatively, the missing shell could point to the nature of the explosion itself. Maybe the event was not a sudden, violent detonation, but a gentler, sustained outflow of energy, a cosmic wind that inflated the bubbles more like a steady breath than a bomb blast. Such a wind would not create the sharp, compressive shock needed for a bright X-ray edge. The third possibility is even more intriguing. It suggests our map of the galaxy is incomplete. The models assume the bubbles are expanding into a uniform, thin gas. But what if the galactic halo is not a placid sea? What if it is instead a turbulent, magnetized, or highly uneven medium? In that case, the bubble's shock could be leaking energy in complex ways, its energy dissipating into a froth of smaller structures instead of focusing into a single, clean shell. The silence at the boundary is louder than any signal. It tells us that the story of the Fermi bubbles is missing a crucial page, one that describes not the fury of their creation, but the quiet, misunderstood nature of the space they call home. This profound silence at the bubble's edge is not the only way it hides its secrets. Deep within its glowing expanse, the structure warps the very fabric of light passing through it, leaving a cryptic signature known as the Faraday rotation anomaly. To understand this, we must think of light not just as a wave, but as a wave with a specific orientation, like a flag fluttering in a specific direction. This is polarization. When this polarized light, especially from distant cosmic beacons like quasars, travels through a region with a magnetic field, something subtle happens. The magnetic field gently twists the orientation of that light, like a slow turn of a dial. The amount of twist measured by astronomers is called Faraday rotation. It is a direct probe, a way to sense the strength and structure of invisible magnetic fields in the vast spaces between stars. Now, when astronomers pointed their radio telescopes at quasars whose light pierced a particular region of the Fermi bubbles, they saw something strange. The amount of Faraday rotation was not just strong, indicating a powerful field. It was strangely patterned, inconsistent, and twisted in a way that defies a simple, uniform magnetic field. The light was not just being rotated, it was being scrambled. This anomaly is a ghostly fingerprint. It tells us that the magnetic field inside that part of the bubble is not a neat set of parallel lines. It is a turbulent, tangled mess, a cosmic knot of magnetic force. Imagine trying to look through a window made not of clear glass, but of countless tiny, twisted crystal fibers, each bending the light a different way. The view on the other side would be distorted in a complex, unpredictable manner. That is what the Faraday rotation data reveals, a region of incredible magnetic complexity. But the true mystery is the cause of this specific tangle. Is it the remnant of violent turbulence from the original explosion, like the choppy wake behind a ship frozen in time? Or is it evidence of an ongoing process, perhaps magnetic fields from the bubble interacting with and shearing against older galactic fields, creating a zone of fierce, invisible friction? The geometry of this magnetic snarl is unknown, a three-dimensional puzzle we can only infer from the two-dimensional twist it imprints on distant light. This single anomaly proves the bubbles are not just energetic, but magnetically sophisticated, hiding layers of invisible structure that challenge our ability to map the forces that truly shape them. The tangled magnetic fields within the bubbles create a hostile furnace of energy, a place where matter should be vaporized into a uniform, superheated plasma. Yet against all odds, life persists in this inferno. Woven through the searing glow are delicate threads of cold, a network of long, thin filaments detected not in gamma rays, but in the gentle ultraviolet light of ancient stars. These are the so-called cool gas filaments, and their very existence here is an act of defiance. Picture finding delicate strands of ice perfectly intact, weaving directly through the heart of an active volcano. That is the scale of this paradox. These filaments are not hot. They are composed of relatively cool, dense hydrogen gas, the basic fuel for star formation, threading their way through the bubble's million-degree plasma. Their survival is the central mystery. In an environment this violent, such delicate structures should be obliterated in an instant, evaporated by the intense heat or shredded by turbulent magnetic forces. The fact that they are not only present but appear as coherent, thread-like strands tells us something extraordinary is shielding them. One possibility is that they are not ancient survivors of the original event but recent interlopers. Perhaps they are tendrils of gas from the galactic disk below, newly drawn up into the bubble's expanding structure, caught so recently that the destructive heat hasn't had time to erase them. This would make them fleeting witnesses, cosmic mayflies living their brief lives in a furnace. The more profound explanation, however, involves an invisible shield. These cool filaments may be cradled and protected by powerful magnetic fields. We know magnetic fields can act as barriers, confining and insulating gas, preventing it from mixing with the surrounding inferno. It is possible each filament is like a wire in a cosmic cable, its cool gas sheathed in a tube of magnetic force that repels the scorching plasma around it. This turns them from mere curiosities into vital clues. If magnetic fields are preserving them, then the geometry of these cold threads is actually tracing the hidden architecture of the bubble's magnetism. Each filament is a drawn line on a blueprint we cannot otherwise see. Their delicate persistence suggests the bubbles are not a formless cloud of destruction, but a highly structured ecosystem with protected pathways and sheltered zones where the old, cold galaxy can still endure within the new, raging one. This delicate network of cold filaments reveals a hidden order, but the overall shape of the Fermi bubbles is anything but symmetrical. When you step back and look at the entire structure, a glaring imbalance emerges. The southern bubble's foundation is noticeably broader and more diffuse than its northern counterpart, as if the entire southern structure is melting into the galaxy below. This is not a minor imperfection. In a cosmos often governed by clean, opposing forces, such a pronounced asymmetry is a clue written in the negative space. It demands an explanation, and astronomers have two leading, competing theories, each pointing to a different chapter in the galaxy's violent history. The first theory looks to the environment, suggesting the bubbles are not expanding into a perfect vacuum. The galactic disk below is a messy place filled with uneven clouds of gas and dust. Imagine trying to inflate two identical balloons, but you place one on a smooth table and the other in a pile of soft pillows. The balloon on the pillows will spread out, becoming wider and flatter at its base. This could be the fate of the southern bubble. If the region of the galactic disk it is erupting from was particularly dense with interstellar material, that dense gas would act as a resistance, causing the bubble's energy to spread sideways as it fought to push upward. The southern bubble's broad, diffuse base, then, would simply be a map of an ancient cosmic obstacle course. The second theory is far more dramatic. It proposes the asymmetry was baked in from the very first moment of creation. What if the eruption from the galactic center was not a clean, symmetrical burst, but a fundamentally lopsided event? Our supermassive black hole, Sagittarius, a star, might have had an uneven feast. Perhaps a large cloud of gas fell in from one particular direction, or a star was torn apart on a skewed orbit, triggering a jet that was more powerful on one side than the other. In this scenario, the southern bubble was simply born bigger and messier, its broader base the permanent scar of an intrinsically unbalanced explosion. This lopsidedness forces us to ask a deeper question about the bubble's origin. Are we seeing the aftermath of a single titanic burp from the black hole, or could it be the accumulated effect of many smaller, uneven outbursts over millions of years, with the southern side receiving just a little more energy each time? The asymmetric base is a permanent tilt in the scales of this mystery, a reminder that the story of our galaxy's heart is not one of perfect balance, but of chaotic, messy violence. This lopsided shape is a clue written in the bubble's very posture, but the true nature of its power is written in a language of pure energy. Deep within the Fermi bubbles, there exists a pattern so strange it has its own name, the high-energy electron spectrum. This is not a physical shape you could draw. It is a statistical fingerprint, a detailed chart showing exactly how many electrons are moving at each possible speed, from the relatively slow to the nearly impossible. And this chart tells a story that breaks the rules. When cosmic rays are accelerated by normal processes like the shock waves from a supernova, they produce a predictable pattern. Think of it like a natural slope. Most of the particles gain a moderate amount of energy, forming a gentle hill on the graph, while only a very few get catapulted to the highest tiers. The spectrum inside the Fermi bubbles does not follow this gentle slope. Its line is steep and relentless, a cliff face rather than a hill. It is what physicists call a hard spectrum, meaning it is astonishingly rich in the highest energy electrons. There are simply too many particles screaming along at nearly the speed of light. It is as if you shook a box of marbles and found that instead of most settling at the bottom, a huge number were magically levitating at the very top. This overabundance of extreme particles is a direct challenge. Standard shockwave acceleration, the workhorse of cosmic particle physics, cannot produce this effect so efficiently across such a vast volume. Something else, something far more potent and mysterious, is acting as a particle accelerator on a galactic scale. This unknown mechanism must not only inject immense energy, but it must do so in a way that preferentially boosts particles to the very highest tiers, skipping the intermediate steps. One tantalizing possibility involves magnetic reconnection, a process where magnetic field lines break and reconnect, releasing enormous energy in a sudden, focused burst, like a cosmic short circuit. This can accelerate particles to extreme energies very efficiently, but to explain the bubble-wide hard spectrum, this reconnection would need to be happening everywhere, a continuous storm of magnetic lightning within the bubbles. Another, more profound idea is that we are seeing the decay products of something even more exotic, perhaps particles of dark matter annihilating each other and flooding the bubbles with this specific hard spectrum of electrons. The high-energy electron spectrum is the bubble's energy budget, and its numbers do not add up. They point to an engine of unimaginable power still running in the shadows, whose fundamental mechanics remain a blank page in our textbooks. The hard electron spectrum reveals an engine of immense power, but its light must escape through a final, luminous membrane. Encasing the entire structure is a thin, brilliant skin known as the synchrotron shell. This is not the missing X-ray shell we searched for earlier. This is something else entirely, a veil of light created by the dance of electrons in a magnetic prison. Those high-speed electrons, the very ones with the impossible energy spectrum, do not travel in straight lines. As they race through the bubble's magnetic fields, they are forced into a spiral, a relentless corkscrew path. And this violent change of direction has a cost. It makes them shed energy in the form of a specific, piercing light, synchrotron radiation. This process paints the bubble's outer layer with a soft, pervasive glow. But the nature of this skin is what deepens the mystery. It is not a fuzzy, uneven boundary. observations show it to be remarkably uniform and possessed of a surprisingly sharp edge, like the surface of a soap bubble held against a dark sky. This sharpness is the critical clue. For the synchrotron skin to be so well defined, two conditions must be met with impossible precision. First, the sea of high-energy electrons must be distributed in a smooth, even sheet right at the bubble's outer limit. Second, and more importantly, the magnetic fields that force those electrons to spiral must themselves be organized into a large-scale, coherent structure that lines the entire surface. Think of it as a magnetic eggshell, a continuous, unbroken layer of force containing the bubble's fury. Generating such a thing is a profound puzzle. Magnetic fields in space tend to be messy, tangled things, especially after a violent event. They fray and knot and dissipate, creating a smooth, globe-spanning magnetic sheath and then maintaining it for millions of years against the relentless pressure of the hot plasma inside requires a level of order that defies our standard models of cosmic explosions. It suggests the original event did not just blast material outwards, it somehow imprinted a perfect magnetic architecture on that material, a blueprint that has held firm across eons. This luminous skin is therefore more than a boundary. It is a preserved fossil of the event's first moment, a snapshot of a force so organized it could wrap chaos in a cloak of perfect, glowing geometry. What kind of eruption thinks in spheres and leaves behind a magnetic sculpture of itself? That luminous magnetic skin defines the bubble's present shape, but etched faintly within its volume are the ghosts of past eruptions. These are the infrared loops, vast and subtle structures that appear only when we view the sky through the specific eyes of infrared telescopes. They are not the brilliant gamma-ray arches or the searing X-ray knots. Instead, they are colossal, faint ribbons of warmth curling through the bubbles like the faded scars of ancient violence. Two major loops have been identified, each spanning thousands of light years, their gentle curvature suggesting they might outline the boundaries of much older shock waves or trace the paths of dormant magnetic field lines. Seeing them requires looking at just the right wavelength of infrared light, one that is emitted by cold dust grains gently heated by starlight or by the faint glow of molecular hydrogen gas. This specific visibility is the first clue to their nature. They are not made of the hot, frenetic plasma that fills the bubbles today. They are composed of cooler, more settled material, the cosmic soot and ash left behind after a fire has died down. Their loop-like shape points directly to a history of expansion. When a shock wave from an explosion moves through space, it can sweep up surrounding gas and dust, compressing it into a shell. As that shell expands and ages, it cools and fragments, but portions of it can remain as coherent arcs, like pieces of a shattered soap bubble still holding their curve. These infrared loops could be exactly that, the fossilized remnants of shock fronts from earlier, smaller outbursts from the galactic center that occurred long before the main event that created the Fermi bubbles we see now. They would be chapters from an older history book preserved within the newer volume. Another compelling idea is that they are not shock fossils at all, but magnetic footprints. Powerful magnetic fields can guide and confine charged particles, and over time, dust can align along these invisible lines of force. The loops may be tracing out the architecture of the bubble's magnetic skeleton in the slowest, most passive way possible, using dust as a tracer to illuminate the hidden framework. Their faint, infrared-only glow suggests they are not actively powered, but are instead illuminated by the ambient light of the galaxy, like fog illuminated by distant streetlights. This connects them to a deeper rhythm of galactic life. If they are indeed relics of past activity, they tell us the heart of the Milky Way does not erupt in a single, unique catastrophe. It beats with a slow, arrhythmic violence, coughing out bubbles and shocks every few million years. The Fermi bubbles would then be merely the largest and most recent example, with these infrared loops serving as the faded echoes of their predecessors. They force us to wonder, are we seeing one event or the layered archaeology of many? each outburst writing its signature in a different kind of light on the same crowded sky. These faint infrared echoes suggest a history of repeated violence, and deeper within the main bubbles, we find the voids that prove it. Scattered like cosmic pockets of silence are three distinct regions known as the sub-bubble cavities. They are not bright structures, but rather dark ones, zones where the gamma-ray and X-ray glow that fills the rest of the Fermi bubbles suddenly dims and fades. These are not mere gaps in a cloud, they are structured absences, spherical hollows carved into the luminous fog. Picture a massive soap bubble, and within its shimmering film, you see three smaller, perfectly formed voids like bubbles trapped inside a bubble. That is the geometry we are observing. Their existence transforms our understanding of the timeline. If the Fermi bubbles were the product of a single, brief explosion from the galactic center, we would expect a relatively smooth, uniform interior like the inside of a balloon. These cavities shatter that simplicity. They are evidence of a stop-start, episodic violence. The most compelling explanation is that we are seeing the layered remnants of multiple, distinct outbursts. Imagine our supermassive black hole, Sagittarius, a star, experiencing a major eruption that blows out the first, largest bubble. Then, after a period of quiet lasting perhaps hundreds of thousands of years, it erupts again with a slightly different orientation or power. This second, younger explosion expands within the still-present shell of the first, its leading shockwave pushing aside and reheating the older material, but leaving behind a pocket of relatively undisturbed space, a cavity from its earlier phase. A third, even later eruption could then create another cavity within that. We are not looking at one event, but at a geological record of galactic tantrums, each outburst fossilized within the glow of the next. The dim emissions within these voids are the key clue. They represent the cooler, more settled plasma that was there before the most recent eruption came through and energized everything around it. These sub-bubble cavities are the negative spaces in a sculpture of violence, and their silent presence argues that the heart of our galaxy does not sleep, it merely rests between fits of rage. These cavities of quiet history are not the only way the bubbles record time. There is a more subtle clockwork ticking within their vast volume, written in the flow of invisible atomic bullets. This is the anomalous cosmic ray gradient, and it is a pattern that should not exist. Cosmic rays are not rays of light, they are physical particles, mostly protons and atomic nuclei, hurtling through space at nearly the speed of light. When we map their density inside the Fermi bubbles, we expect to see a simple story. If the bubbles were inflated by a single, ancient explosion, the cosmic rays inside should be smoothly distributed. They should be most concentrated near the center where the event occurred and gradually fade toward the edges, like the scent of perfume diffusing from an opened bottle. The reality is a jagged, complicated mess. The intensity of these high-energy particles does not follow that gentle gradient. Instead, it changes in sharp, non-uniform steps with unexpected peaks and valleys scattered throughout the structure. In some regions near the edge, the cosmic ray density is surprisingly high, as if there is a fresh source pumping particles directly into the bubble's outer layers. In other areas closer to the galactic center, the density can be oddly low, like a hollow pocket within the storm. This messy pattern is a direct contradiction. A single, short-lived explosion from Sagittarius, a star, would have created a smooth, expanding cloud of cosmic rays, its edges slowly mixing with the quieter galaxy beyond. The anomalous gradient we see tells us that simple model is broken. It suggests the injection of these particles is not a one-time event, but an ongoing or fantastically complex process. One possibility is that the bubbles are being continuously fueled. Perhaps a steady wind from the galactic center, far weaker than a cataclysmic blast but persistent over millions of years, is still blowing cosmic rays into the structure, creating fresh hotspots and an uneven distribution. Another, more turbulent idea involves the bubble's own magnetic architecture. Those tangled magnetic fields we detected through Faraday rotation could be acting as a labyrinthine particle accelerator. Cosmic rays might not simply diffuse outward, they could be trapped, reflected, and re-accelerated within magnetic pockets, creating local concentrations of intensity that defy any smooth gradient. This turns the bubbles from a fossil into an active machine. The anomalous gradient is its current, uneven hum of operation. It means the story of the Fermi bubbles is not written in a single chapter of violent birth, but in an ongoing sentence, one where the engine of our galaxy's heart is still, quietly, writing its signature in a rain of atomic shrapnel. That uneven rain of cosmic rays points to an invisible maze, a labyrinth of force whose true shape has only been glimpsed in fragments. The 23rd structure is not seen with light at all, but inferred from the subtle warping of it, a phenomenon revealing the magnetic field braids. We have already encountered hints of this tangled complexity through the Faraday rotation anomaly, a scrambling of distant starlight, but newer, more detailed polarization studies paint an even more astonishing picture. The magnetic fields within the Fermi bubbles are not a neat set of parallel lines like the orderly field around a simple bar magnet. Instead, the data suggests they are twisted, intertwined, and braided together like three strands of rope woven into a single, chaotic cable. This braiding is a signature of extreme turbulence and shear, a state of magnetic energy so complex it defies simple mapping. How could such intricate braids form on a scale of tens of thousands of light years? The answer lies in the dynamics of the original outflow. Picture the event not as a clean explosion, but as a prolonged, churning wind erupting from the galactic center. As this wind expands, different streams within it move at slightly different speeds. These shearing layers, rubbing against each other, would twist the magnetic fields frozen within them, just as you can twist the strands of a rope by rolling them between your palms. Over time and across vast distances, these simple twists can become complex braids. Another possibility involves the interaction of multiple eruptions. If the bubbles were built by several outbursts from the black hole, as the sub-bubble cavities suggest, then each new eruption would inject its own magnetic field into the mix. These successive fields, each with a different orientation, would tangle with the older ones, weaving together into a messy, layered braid. The implications of this braided structure are profound for the bubble's internal ecosystem. A braided magnetic field is not just a passive scaffold, it is an active component. These complex field lines can act as conduits and traps for high-energy particles, channeling them along specific paths and explaining the jagged cosmic ray gradients we observe. They can also store immense energy through their twists and kinks, energy that might be suddenly released in bursts of magnetic reconnection, those cosmic short circuits that could power the gamma-ray hotspots and keep the sea of electrons energized. This means the Fermi bubbles are not a fading relic with a static magnetic skeleton. They are a dynamic, seething volume where magnetic energy is constantly being transferred, stored, and released in a slow-motion storm. The braids are the visible, or rather inferable, manifestation of that ongoing storm, a permanent record of the chaotic violence that birthed them and a continuing engine for the strange phenomena we see within. These magnetic braids knot downwards, anchoring the entire structure to a violent birthplace. At the very base of the southern Fermi bubble, merging with its diffuse lower boundary, lies a smaller but fiercely energetic structure known as the galactic center lobe. This lobe is not a part of the bubble proper, but a distinct entity, a dense and turbulent plume of radio waves that rises like a twisted pillar from the galactic plane directly below Sagittarius, a star. It is a known feature, a local disturbance in the galaxy's stormy core, but its placement is uncanny. It appears to be the literal root from which the southern bubble grows, a thick stem feeding into an impossibly vast canopy. This intimate connection forces a pivotal question. Are we looking at cause and effect? One compelling school of thought sees the lobe as the direct precursor, the opening act of the cataclysm. In this narrative, the event began not with a single detonation, but with a sustained, focused eruption from the black hole or a cluster of violent star formations around it. This initial outburst blew the galactic center lobe upwards, a jet of concentrated energy that punched through the densest gas of the galactic disk. Once this jet cleared a path, breaching the thickest layers of interstellar material, the pressure behind it was released in a far broader, more explosive fashion, inflating the gargantuan Fermi bubble above it. The lobe then would be the drill bit and the bubble the cavern it hollowed out. This is a clean, sequential story, yet other astronomers see a different relationship. Could the lobe and the bubble be entirely separate events, merely superimposed by our line of sight? The galactic center is a crowded, violent neighborhood with outbursts likely occurring every few million years. It is statistically possible that a smaller, more recent jet created the lobe, and it simply happens to be projecting against the backdrop of the much older, larger bubble, creating an illusion of connection where none exists. The final and most dramatic possibility is that they are simultaneous products of the same colossal mechanism. Perhaps the original event was not a clean jet or a spherical explosion, but a fundamentally messy and asymmetric release of energy. In this scenario, the bulk of the energy went into inflating the diffused bubbles, while a narrower, more concentrated stream of magnetized plasma was focused by chaotic physics into the dense, structured form of the lobe. They would be siblings, not parent and child, born from the same chaotic birth. The evidence lies in their detailed chemistry and magnetic signatures. If the lobe's gas composition and the pattern of its magnetic fields match those found in the base of the southern bubble, the link is likely real. A mismatch would suggest separate origins. This smaller lobe is therefore a critical key, a tangible piece of the galactic center we can study up close, and its relationship to the bubbles will ultimately tell us whether we are seeing a single, monstrous breath from the galaxy's heart, or the layered echoes of its chronic, ragged coughs. The dense, turbulent galactic center lobe points directly to a specific kind of violence, a focused beam of pure power. This leads us to the most elegant and terrifying explanation for the entire structure, the ghost jet theory. Imagine our supermassive black hole, Sagittarius a star, not as a quiet object but as an active quasar's heart blazing with light. Millions of years ago, it may have feasted on a vast cloud of gas or a swarm of stars. In such a frenzy, black holes do not just swallow matter, they often fire it back out. Twin beams of magnetized plasma, moving at almost the speed of light, can erupt from its poles, punching through space in perfectly straight lines. These are relativistic jets, and we see them powering brilliant quasars and active galaxies across the universe. The ghost jet theory proposes that the Fermi bubbles are the faded, expanded remnants of just such a pair of jets from our own galactic center, a quasar episode in our distant past. The structural evidence is compelling. The bubbles are not spheres, they are elongated lobes taller than they are wide, aligned almost perfectly perpendicular to the galactic disk, exactly the orientation you would expect for jets fired from a spinning black hole. Their symmetry, north and south, mirrors the expected symmetry of bipolar jets. Even the subtle lopsidedness we see could be explained by the jets interacting with an uneven galactic atmosphere, like two fire hoses hitting slightly different patches of ground. This model elegantly explains the bubble's sheer scale and their crisp edges, as a relativistic jet would carve a clean tunnel through space, its leading shock inflating a massive cavity as it went. Yet for all its elegance, the ghost jet theory faces serious challenges. The first is a matter of energy. The Fermi bubbles are immense, requiring a phenomenal output from Sagittarius a star. While possible, it demands a feeding event of staggering proportions, one that would have made the galactic center outshine every star in the Milky Way for tens of thousands of years. We see no obvious remnant of such a brilliant cataclysm in the surrounding stars or gas. The second, more technical challenge involves the bubble's contents. Relativistic jets are typically narrow, pencil-thin beams of ultra-fast particles. The material inside the Fermi bubbles, however, is not streaming out in a narrow column. It is a more or less filled in volume of hot plasma. This suggests that if jets were the trigger, they must have later inflated these wider bubbles, perhaps by dragging surrounding gas with them or by spreading out after they stopped. The final and perhaps greatest challenge is time. A jet event is thought to be relatively short-lived, perhaps lasting only a few tens of thousands of years. Could the inflated bubbles and all their intricate internal structures like the magnetic braids and the gamma-ray hotspots remain so bright and well-defined millions of years after the engine shut off? It would require a perfectly balanced act of preservation, like a smoke ring holding its shape in a perfectly still room for centuries. The ghost jet theory gives us a powerful, familiar culprit, but it leaves us wondering if our black hole's past fury was truly sharp enough to carve such lasting, detailed scars. The ghost jet theory relies on known physics, but the Fermi bubbles may be hiding evidence of the universe's greatest unknown. A shadow falls across the entire investigation, the possibility of a dark matter annihilation signal. This is the most speculative yet profoundly consequential explanation for the bubble's persistent glow. Dark matter is the invisible scaffolding of the cosmos, a substance that outweighs all visible stars and gas by a factor of 5 to 1. We know it exists through its gravitational pull, but we have never directly detected a single particle of it. Many theories predict that dark matter particles could be their own antimatter opposites. If this is true, when two such particles collide, they would annihilate each other in a flash of pure energy, producing a cascade of secondary particles, including gamma rays. The dense, turbulent environment at the galactic center is theorized to be one of the best places in the galaxy to spot this process, as dark matter should be concentrated there. Proponents of this idea point a finger directly at the gamma-ray spectrum of the Fermi bubbles, especially from the diffuse haze and certain hotspots. They argue that the light contains subtle bumps, specific excesses of gamma rays at very precise energy levels. These are not broad swaths of light, but sharp, spectral lines that could be the fingerprint of a specific dark matter particle mass, like a barcode for an unknown substance. If correct, this would be the first indirect detection of dark matter's true nature, a discovery that would shatter modern physics. The counter-arguments from the broader astrophysics community, however, are formidable. Critics maintain that these spectral features are not clean or conclusive. The alleged bumps could easily be produced by a complex combination of mundane astrophysical processes we do not yet fully understand, like the collective emission from thousands of faint, unresolved pulsars or from unusual cosmic ray interactions in the bubble's unique magnetic environment. The galactic center is a messy place, and attributing a signal to exotic physics requires ruling out every possible ordinary explanation, a bar that has not yet been met. The debate is a high-stakes standoff. One side sees the potential key to the universe's hidden majority, a signal written in the bubble's very essence. The other sees the human tendency to find patterns in cosmic noise, a classic case of wishing for a revolution where only complex astrophysics exists. This controversy ensures the Fermi bubbles are more than a galactic mystery. They are a frontier in the search for reality's deepest secrets. That dark matter debate searches for answers in the invisible, but a far more tangible culprit might be responsible, one built from the very stars we can see. The starburst wind chimney theory offers a radically different origin story, one where the black hole is not the prime actor but a bystander to a city-wide fire. Imagine the very core of our galaxy not as the domain of a single monster, but as a spectacularly dense metropolis of stars, a place where millions of suns are packed into a region just a few hundred light-years across. Now imagine a period in the galactic past, perhaps 6 or 7 million years ago, when this stellar city experienced a frenzied baby boom. Not just a few new stars, but a colossal, simultaneous burst of star formation. In such a starburst, the most massive stars live fast and die young. They burn through their fuel in mere millions of years, ending their lives as supernova. But even before they explode, these giant stars blast out powerful winds, streams of charged particles flowing from their surfaces at millions of miles per hour. In a normal, quiet region of space, these winds dissipate, but in an ultra-dense stellar nursery they combine. The collective effect is a hurricane. The combined stellar winds and supernova shockwaves from thousands of these massive stars would merge into a single, overwhelming outflow, a superwind. This is not a narrow jet, but a broad, hot, turbulent gale erupting from the entire central star-forming region. This superwind, with nowhere else to go, would blow upwards and downwards perpendicular to the crowded galactic disk. It would carve a channel through the surrounding gas, a giant chimney, venting the furious energy of the starburst out of the galaxy. The Fermi bubbles in this model are the glowing walls of that chimney, the shock-heated and magnetized remnants of that ancient star-driven hurricane. Several structural features align beautifully with this story. First is the sheer breadth of the bubble's bases. A black hole jet tends to be narrow and focused, but a superwind from a vast region of star formation would naturally be wide, explaining why the bubbles merge so diffusely with the galactic plane. The bubbles are not pencil lines, they are the shape of a broad exhaust plume. Second is the chemical fingerprint. The material inside the bubbles, as measured by its X-ray emission, shows an abundance of elements like oxygen, neon, and magnesium. These are precisely the elements forged in the cores of massive stars and then scattered into space by their winds and supernova explosions. It is the expected chemical signature of a stellar population, not necessarily of a black hole accretion disk. Third is the diffuse, filled-in nature of the bubble's interior. A superwind is inherently messy and turbulent, a churning mix of hot gas from countless sources. This matches the observed complex interior of the bubbles, the braided magnetic fields, the uneven cosmic ray gradients, the pockets of cooler gas far better than the more streamlined interior a clean jet might leave behind. The starburst wind model paints an epic, democratic picture of creation. It suggests the Fermi bubbles are not the scar of a single entity's rage, but the collective signature of an entire generation of stars, living and dying together in a brief, glorious frenzy that reshaped the galaxy's atmosphere. This democratic wind from a generation of stars offers a compelling origin, but a single, stubborn observation threatens to dismantle every static model. Some of the gamma-ray light from the Fermi bubbles seems to flicker. The evidence is subtle, buried in years of data from the Fermi Space Telescope, and it remains hotly contested. Yet the mere possibility ignites a firestorm of implications. Gamma rays are the signature of the most energetic processes in the universe. If their glow from the bubbles is changing, even by a tiny percentage over several years, it means the structures are not a fossilized remnant of an ancient explosion. It means they are alive. An active structure requires a continuous power source, a persistent engine that is feeding energy into this vast volume in real time. This would instantly invalidate any model that relies on a single, short-lived cataclysm millions of years in the past. A fossil does not twitch. A static bubble of hot gas, left to slowly cool and mix with the galaxy, would produce a gamma-ray glow that fades with glacial slowness, imperceptible over a human lifetime. Detected variability, however slight, would be a seismic event in our understanding. It would point a definitive arrow toward an ongoing process. The prime suspect would immediately become our supermassive black hole, Sagittarius, a star, not in its dramatic quasar past, but in a quieter, steadier mode of operation. Perhaps it is not feasting in grand banquets, but steadily sipping on a wind of gas from its surroundings, generating a persistent but lower power outflow that constantly re-energizes the bubble's particles. Alternatively, the variability could be tied to the bubble's own complex magnetic anatomy. Those braided magnetic fields might be prone to sudden reconnection events, localized bursts of energy that flash like magnetic lightning within the vast structure, briefly brightening a small region before fading away. Even the starburst wind model would need a drastic revision, requiring not a one-time frenzy of star death, but a prolonged period of activity that has somehow sustained itself for millions of years. The temporal variability puzzle is the ultimate test. It asks a binary question with no comfortable middle ground. Are the Fermi bubbles a majestic tombstone for a forgotten galactic event? Or are they the breathing, shifting evidence of a permanent storm raging at the heart of our home? The flickering light debate forces us to ask what we are truly seeing, and the answer changes depending on the eyes we use. This is the multi-wavelength mismatch, a problem of cosmic perspective. The Fermi bubbles do not have a single true appearance. Instead, they are a chameleon, shifting form and structure as we observe them across different bands of the electromagnetic spectrum. The gamma-ray map from the Fermi telescope shows those vast, glowing lobes with their sharp edges and internal hotspots. Switch to an X-ray observatory and the picture transforms. The brilliant, uniform bubbles fade, replaced by that searing central knot and perhaps faint, wispy structures that bear little resemblance to the gamma-ray silhouette. Point a radio telescope at them, and you see the polarized lobes and perhaps the faint echo of the synchrotron shell. Look in microwaves, and you see the smooth, diffuse haze patches. Each wavelength reveals a different layer, a different population of particles, and a different physical process at work. Trying to align these maps is like trying to superimpose the blueprint of a building, a thermal image of its heating system, and a photograph of its electrical wiring. The lines never quite match up. This mismatch is not a flaw in our observations. It is the central clue to the bubble's layered complexity. The gamma rays come from the fastest, most energetic electrons slamming into photons of starlight or from collisions of high-energy protons. The X-rays come from gas heated to millions of degrees. The radio waves come from electrons spiraling in magnetic fields. Each process probes a different ingredient in the recipe. The fact that these images do not perfectly overlap tells us the bubbles are not a simple, homogeneous soup. They are a stratified ecosystem. The highest energy particles might be concentrated in specific magnetic traps, creating the gamma-ray hotspots, while the million-degree gas might fill broader, quieter regions visible only in X-rays. The microwave haze, a sea of slightly slower electrons, could permeate it all like a fog, independent of the sharper structures. This means there is no single event to explain. We must explain a symphony of events, a coordinated set of processes that populated these vast volumes with different kinds of energy in different distributions. It forces astronomers to build models that are not just powerful, but intricately layered, capable of explaining why one kind of light paints an arch and another reveals only a diffuse glow. The multi-wavelength mismatch is the final, sobering reminder that the Fermi bubbles are not a puzzle with one missing piece. They are a vast, three-dimensional jigsaw where every piece is a different color from a different box, and we are only just beginning to understand the picture they are meant to form. Every map we have is a portrait of the interior, a catalogue of the chaos within. But the true frontier of the Fermi bubbles lies beyond their luminous skin, in a place we cannot yet see. This final, theoretical structure is not a filament or a knot. It is the ultimate boundary shock, the invisible wall where the entire system slams into the silent void of intergalactic space. If the bubbles are a ship, this is its bow wave, a titanic ripple of force plowing through the thin gas of the galactic halo. Its existence is demanded by physics. Any structure expanding at supersonic speeds into a medium, even one as diffuse as the intergalactic gas, must create a shock front, a sharp boundary where material is compressed, heated, and swept aside. This shock would be the final and most definitive signature of the bubble's raw power, a cosmic sonic boom frozen in space. Yet despite our most sensitive telescopes scanning in X-rays and radio waves, this brilliant rim remains elusive. Its absence is the last great observational silence. The failure to detect this shock is not a failure of our instruments, but a profound clue about the bubbles themselves. One possibility is that the shock has already passed. The bubbles may be so ancient that their initial explosive expansion has slowed to a subsonic crawl. In this scenario, the sharp, energetic shock wave dissipated millions of years ago, leaving behind a gentle pressure wave that pushes against the galactic halo too softly to create the brilliant X-ray emission we are searching for. The bubbles would be cosmic ghosts, expanding so slowly their passage is silent. Another, more intriguing idea is that the intergalactic medium is not the placid sea we assume. It might be a turbulent, magnetized, and highly uneven froth. A shock wave plowing into such a messy environment would not form a clean, bright shell. Instead, its energy would dissipate into a complex network of faint ripples and turbulent eddies. Its light spread so thin our telescopes cannot pick it out from the background glow of the universe. The shock might be there, but shattered into a million pieces. Finding this ultimate boundary would answer the most fundamental questions. Its distance from the galactic center would give us a precise clock, revealing the exact age of the bubbles. The temperature and brightness of the shocked gas would act as a cosmic dynamometer, measuring the total energy of the original cataclysm with unprecedented accuracy. We could finally weigh the explosion. More profoundly, detecting the shock would tell us what lies beyond. It would map the true edge of the Milky Way's atmosphere, revealing the density and structure of the galactic halo we call home. We would see, for the first time, the actual boundary where our galaxy's influence meets the vast, empty currents of intergalactic space. The search for this final shock is therefore a search for a wall in the dark. Its discovery would frame the entire mystery, placing a definitive border around 30 structures of unexplained light, and confirming that the story of the Fermi bubbles is not just an internal affair, but a permanent alteration to our galaxy's place in the cosmic ocean. So we have a zoo of cosmic oddities, from magnetic braids to cold filaments, all trapped inside two glowing bubbles. The real mystery is not any single structure, but their impossible coexistence. How can one event create both delicate threads of cold gas and a sea of the highest energy particles? The answer lies not in choosing one clue, but in weaving them all into a single story. Two grand theories stand as competing frameworks, each trying to explain this entire chaotic menagerie. The first is the ghost of a black hole jet. This elegant model sees the supermassive black hole, Sagittarius, a star, as the sole sculptor. In this story, a past eruption fired twin beams of magnetized plasma directly up and down from the galactic plane. These jets would act like cosmic blowtorches, carving clean tunnels and leaving behind the bubble's sharp edges and symmetrical lobes. This theory excels at explaining the large-scale architecture. The bubble's perfect alignment perpendicular to the galaxy, their elongated shape, and even the potential for that organized magnetic sheath all fit the jet narrative beautifully. A powerful, focused jet could also accelerate particles to the extreme energies we see in the hard electron spectrum. But the jet model begins to strain when confronted with the zoo's finer details. Why is the southern bubble's base so diffuse and messy if a jet is a precision instrument? How does a narrow beam explain the vast, filled-in volume of the bubbles or the survival of those fragile, cool gas filaments? A jet is a surgeon's scalpel, but the interior of the bubbles looks like the aftermath of a tornado, a chaotic mix that includes preserved relics. The jet might have been the trigger, but did it alone create this entire preserved ecosystem? The second grand theory offers a more democratic and chaotic origin. The starburst wind chimney does not rely on a single monster, but on the collective fury of an entire generation of stars. Imagine the galactic center 7 million years ago as a stellar metropolis experiencing a frenzied baby boom. Thousands of massive stars, living fast and dying as supernova, would have combined their ferocious winds into a single galaxy-shaking gale. This superwind would blast outwards in a broad plume, not a narrow beam, naturally explaining the bubble's wide bases and their filled-in turbulent interiors. This model is a natural fit for the chemical evidence. The abundance of elements like oxygen and magnesium found within the bubbles is the specific fingerprint of massive stars and supernova. The chaotic magnetic braids and the pockets of cooler gas also make more sense in a turbulent superwind than in the streamlined wake of a jet. The wind is inherently messy, a churning mix that could both accelerate particles and also shield older structures, preserving the cold filaments within magnetic pockets. Yet the starburst wind faces its own monumental challenge: energy. To inflate structures as vast and energetic as the Fermi bubbles requires an almost inconceivable amount of power. Was there truly such a colossal, coordinated burst of star formation in our galaxy's recent past? And could such a wind create the crisp, sharp edges we observe, or the large-scale magnetic order implied by the synchrotron shell? A hurricane does not usually leave behind perfectly defined boundaries. The truth may lie in a hybrid, a messy marriage of these two titanic forces. Perhaps the story is not one or the other, but both in sequence. An initial, weaker starburst wind might have cleared a path, creating a chimney through the dense gas of the galactic disk. This preparatory work could have then allowed a subsequent outburst from the black hole, a powerful jet, to travel much farther and faster, inflating the final bubbles within that pre-existing channel. In this scenario, the cool filaments and chemical abundances are relics of the stellar wind phase, while the sharp edges and extreme particle acceleration are the signature of the black hole's final act. Or perhaps the black hole itself was awakened by the turmoil of the starburst, its feast triggered by the same galactic chaos. Evaluating which model best explains the collective zoo forces us to ask what we value most: architectural elegance or explanatory chaos. The jet model gives us a clean, powerful cause for the bubble's shape. The wind model gives us a natural explanation for their rich, complex interior. Neither alone seamlessly accounts for everything. This standoff is the heart of the mystery. The 30 unexplained structures are not just a list of curiosities. They are the 30 pieces of evidence in a cosmic trial, where the defendant is the violent heart of our own galaxy, and the verdict on what truly happened remains, for now, delightfully out of reach. The ultimate verdict on this cosmic trial will rewrite the biography of our galaxy. Solving the mystery of the Fermi bubbles is not just about identifying a past explosion. It is about decoding a fundamental chapter in the life story of every large galaxy, a process known as galactic evolution. These colossal structures are a fossilized record of a critical feedback cycle, a cosmic dialogue of creation and destruction between a supermassive black hole and its stellar surroundings. Understanding this dialogue reveals how galaxies grow, change, and ultimately regulate their own fate. At the heart of this process is a simple, profound question: how does a galaxy keep from becoming too large? Why doesn't the Milky Way, with all its gas and dust, simply form stars in an uncontrolled frenzy until it burns itself out? The Fermi bubbles provide a stunning answer. They are the evidence of galactic self-control. Imagine a vast reservoir of cold gas, the raw material for new stars, flowing toward the galactic center. If this gas accumulated unchecked, it would spark an epic starburst, forming millions of suns in a relatively short time. But this very inflow of gas would also feed the dormant supermassive black hole. As the black hole feasts, it becomes active, launching jets or winds of tremendous energy. Those outflows, which we may be seeing as the Fermi bubbles, then blast back into the surrounding galaxy. They heat the remaining gas, push it away, and disrupt further star formation. It is a cosmic thermostat. Too much star formation fuels the black hole, which then activates to shut down the star formation. This feedback loop is essential. It prevents galaxies from exhausting their fuel in a single, brief blaze of glory, allowing them to live long, structured lives where stars form at a steady, sustainable pace over billions of years. The Fermi bubbles, therefore, are a snapshot of this thermostat in action, a fossilized example of our galaxy hitting the brakes. Their immense energy, whether from a black hole jet or a starburst wind, was the mechanism that heated and cleared gas from the galactic center, quenching star formation there and influencing the chemical enrichment of the entire galactic halo. By studying the bubble's age, energy, and contents, we can measure the strength of this feedback event. We can ask how much gas was expelled, how many potential stars were never born because of this outburst. The answers tell us how our Milky Way managed its resources and shaped its current, relatively quiet state. Furthermore, the bubbles are a time capsule of the galactic center's environment from millions of years ago. The chemical elements trapped within their glow, like oxygen and magnesium, are the ashes of specific types of stars. By analyzing these, we can reconstruct the population of stars that existed in the galactic core just before the cataclysm. Were they mostly short-lived, massive stars whose deaths drove a superwind, or is the chemistry more consistent with material processed by a black hole's accretion disk? This forensic analysis lets us read the history written in that light, telling us not just what happened, but what the neighborhood was like before it happened. On the largest scale, the Fermi bubbles demonstrate that galaxies are not static islands of stars. They are dynamic ecosystems breathing and erupting over cosmic time. The energy from their cores can reach far beyond the visible disk, inflating enormous cavities that permanently alter the galactic atmosphere. This means the evolution of a galaxy is not just about the stars within it, but about the vast, invisible volumes of hot gas that surround it. The bubbles show our Milky Way has an atmosphere, a corona, and that this atmosphere can be violently disturbed. Such disturbances affect how a galaxy accretes new gas from intergalactic space and how it might eventually merge with neighboring galaxies. If the Fermi bubbles are a common phase in a galaxy's life, as observations of similar structures in other galaxies suggest, then they are a standard part of cosmic growth. Our home galaxy is not a passive bystander in the universe. It is an active participant, sculpting its own destiny through these colossal outbursts. Solving this mystery gives us the blueprint for that self-sculpting process. It tells us how a galaxy like ours lives, regulates itself, and endures across billions of years, with its central monster and its stellar citizens locked in a dance of furious, beautiful balance. That galactic biography is still being written, and every one of the 30 structures we have explored is a sentence in its pages. From the perfect gamma-ray arches framing the violence to the braided magnetic fields knotting its interior, from the cold filaments defying the inferno to the missing shock at its silent frontier, each anomaly is a clue. Together, they form an overwhelming body of evidence that a monumental event, a fundamental reorganization of forces, once tore through the heart of our Milky Way. We are left not with a single answer, but with a richer, more vibrant mystery. The ghost of a black hole jet and the echo of a starburst wind both whisper from the data, suggesting our galaxy's history is written in both focused fury and democratic chaos. This journey through the Fermi bubbles reveals a cosmos that is not serene, but alive with unresolved energy. It shows us that our home is an active, breathing entity capable of eruptions that sculpt its very atmosphere. So, as this map of unexplained light hangs in your mind, which structure captivated you the most? Was it the elegant southern spiral filament, a twisted rope of pure power? Or the persistent central X-ray knot, that still glowing ember at the crime scene? Share your thoughts and keep looking up with that sense of wonder. The next observation, the next piece of data, could be the one that finally fits, rewriting our galactic story once and for all.